So I'll give you one of mine. If by breath alone I can be a bigger man, how ephemeral. My better ones. All right. So I think I've shown you this picture before of, maybe not, maybe I just have seen it too many times. This diagram of Galen's depiction of the cardiovascular system, its relationship to the heart, the liver, and the lungs. Pardon me. Another excerpt from his writings: blood passing through the lungs, absorbed from the inhaled air, the quality of coolness, which it then carried into the left heart. So this is reprising that idea of Aristotle's of the four elements: the heat, the fire, the water, the air, and the earth, and how the lungs were responsible for cooling the innate heat of the body. He did understand that the lungs were bringing something. The vasculature was transporting something from the lungs to the heart. He recognized that vascular connection there. Leonardo da Vinci got a little bit more into the actual tissue itself. The substance of the lungs is dilatatable and extensible, like the tinder made from a fungus, but it is spongy, and if you press it, it yields to the force which compresses it, and if the force is removed, it accreases again to its original size. So, hinting at the ability of this tissue to change in volume and return to its original state. It was not until we had William Harvey, I think I've also flashed his photo up here before. William Harvey was the first person to begin to understand a little bit deeper the function of the lungs. He believed that the lungs provide some sort of nourishment to the body via the blood. This was still in the era of phlogiston. We were about 100 years yet from the work of Lavoisier and the final banishment of the notion of the four elements from Aristotle. But this guy did understand that something was going on in the air. The lungs were providing some kind of thing that was essential for life. Life and respiration are complementary. There is nothing living which does not breathe, nor anything which breathing does not live. That was in his writings, and there are a few of his drawings of the lungs that he did in careful detail. However, it was not until the 19th century when this guy, Osler, William Osler, did the modern era of pulmonology begin. At that time, it was called physiology. Physiology. Look at that. P-H-T-H-I-S-I. O-L-O-G-Y. Physiology. That is the study of tuberculosis, the treatment of tuberculosis. He founded the National Association for the Study and Prevention of Tuberculosis, which eventually became the National Lung Association. And you can see some of their promotional materials there: careless spitting, coughing, sneezing, spread influenza, and tuberculosis. I read an article in the New York Times today that was telling people to sneeze into their elbow, not their hand. So kind of the same thing. Not much has changed in 100, 200 years. Culture has been subject to the scourge of polio for most of its history. There were various outbreaks of it. There was an extreme outbreak in the late 19th and early 20th centuries. Poliomyelitis led to the deinnervation of diaphragmatic muscles and the inability to breathe. And so there were these people that they became paralyzed, unable to walk, and in fact unable to breathe. So they had these iron lungs, these whole wards. This is Bellevue Hospital right here in Manhattan. They had an entire ward dedicated to these people who were suffering from poliomyelitis. You notice that many of them are little children. We see all these little kids here condemned to spend their lives, at least at the time, in these negative pressure things where the pressure would go down and it would expand their chest, and then the pressure would go up and compress on their chest and thus force the ventilation for these people. This was a kind of nightmarish existence for them, as you can imagine. And Jonas Salk and the polio vaccine was a major medical victory for humanity at the time. So it's all about this, though. The alveoli. This is where we get gas exchange between the atmosphere and our blood. Now, what's interesting about the lungs is in a healthy individual, a non-smoker, non-asthmatic individual, your lungs have approximately 35 times the surface area of your body. So the skin that covers your body, multiply that by 35, and that's the surface area of your lung. The reason this is important is because the surface area is the exchange surface for gas to pass into the blood. And I'm going to take a bit of a conceptual diversion for you just for a moment. Maybe this will help some of you think about the world differently, maybe not. But there is a fundamental principle of the three-dimensional space that we live in, or I guess a more generalizable principle, that you can fit an infinite amount, in theory, you can fit an infinite amount of n-1 dimensional surface inside of a finite n-dimensional surface. So what do I mean by that? I mean in this case, in a finite volume, the volume of your lungs, you can fit theoretically an infinite surface area if you just have that surface area folded up highly and packed into that volume. This principle guides so much of the organization in the natural world around you. Like you'll see it everywhere. For example, snowflakes look like snowflakes because they're maximizing perimeter to surface area, right? If you look at the shape of a snowflake, it has a finite surface area because you can draw a circle around it, but the perimeter of it has all of these little ins and outs, and the perimeter being the one-dimensional surface is heading towards infinity inside of a finite two-dimensional surface. On and on, we can find many examples of it, but this is a beautiful example of it, where the surface area of your lungs is 35 times that of the rest of your body in a tightly confined space of the lungs. All right, well, how does this happen? How does this work? That's going to be the rest of the week. So I'm going to have to talk a little bit about respiratory anatomy and ventilation. This will lead me into talking, I have a slide on asthma and chronic COPD. We'll talk about what that means. And then I'll have to talk about gas exchange, how the gas actually exchanges into the blood. And then all of that is leading me to really the point of the week, the thing that's the most exciting, which we probably won't get to until Wednesday, but that is hemoglobin and how hemoglobin works. Certainly the most complicated protein that we're going to talk about in any detail this semester. And the saturation dynamics for hemoglobin, exactly how that works. And then I'll touch on carbon dioxide transport. If I have time on Friday, I'll hit lung cancer. But the bulk of Wednesday and Friday is going to be focused on hemoglobin and how it actually works. Pretty sophisticated physiology that we'll hopefully find intriguing. So on with the anatomy. Any questions over any of that? All right. In general, the respiratory system is broken into an upper and a lower respiratory system. That boundary is in the larynx. So in terms of the upper respiratory system, you have the nasal cavity and the nasal concha, also known as the turbinates. These bones that look like conchs, and they create turbulence in the air so that, man, it is warm in here, so that odorants, particles that you may be smelling in the atmosphere can adhere to the nasal mucosa and be sensated by the olfactory neurons there. Then we pass from the nasal cavity into the pharynx through the internal nares, N-A-R-E-S. There's the external nares, which are your nostrils, and then the internal nares is how you get out of the nasal cavity into the pharynx. And the pharynx is this dual-purpose compartment between the back of the mouth, the back of the nose, and where both air and food is able to pass through the pharynx, food going down the esophagus, and our breath passing through the larynx into the lower respiratory system, which descends from the larynx via the trachea. The trachea has these semi-annular rings, meaning they're actually incomplete across the back. They're not a full, so your trachea does not have a complete ring of cartilage that goes all the way around. There's a little muscle called the trachealis across the back that can contract and allow for the compressibility of the trachea up to a certain point. And then there's the bifurcation into the primary bronchus, the right and left primary bronchus, which then goes into the bronchial arborization, or the bronchial branching into the two lungs. So the functions of the respiratory system, of course, the nasal cavity is responsible for filtering the air you breathe and olfaction, giving you the sense of smell. Phonation, your ability to speak, is the job of the larynx. In fact, there is a difference here. Phonation is simply the generation of sound, and articulation is the modifying of that sound by the mouth, the oral apparatus. So, for example, if I were to phonate Happy Birthday song without articulating it, it would be ha 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 ha. So I'm just making the sound with my larynx. That's what the larynx does. It phonates. And then the trachea has this charming surface called the mucus elevator. It's this mucus epithelium, the ciliated mucosa, that protects the respiratory surfaces by getting any dust particles and smudge and crud stuck to it, and then the mucus has these cilia that just brush the junk upwards towards the pharynx, where you can expectorate it. And then, of course, the lungs are responsible for gas exchange, and the musculature is responsible for ventilation, or the movement of air to the exchange surfaces. All right, so if you were to look at a cross-section of Jean-Luc Picard's face, you would see the turbinates here, the highly tortuous path through the nasal cavity that mixes the air up and allows you to be able to inhale it. It seems like this is highly tortuous, but in fact, if you, for example, look at the cross-section of a bloodhound or a seal or something like that, those nasal cavities are unbelievably labyrinthine. because they have a much more highly attuned sense of smell, and they're trying to sample odorants much more fully than humans are. All that turbulence is also going to humidify and warm the air to protect the lungs. So here is a picture of the cilia of the mucus elevator I was talking about a moment ago. Particles, pathogens, whatever, is going to get stuck to this mucosa, and then the cilia will just continue to beat and wave and move that mucus along upwards towards the pharynx. This high surface area here is also responsible for continuing to warm that air, so that that air, there's not a temperature gradient between the air in the alveoli in the lungs and the rest of the core temperature. So it's important to do that, and because of that, we have this high surface area that allows for a moistening of the air. Here's a little cartoon that shows the same. So on the left panel, we see that mucosa in perhaps the tracheus, with all of these cilia moving that layer of mucus upwards that has these trapped particles of whatever sort embedded in it, stuck to it. And then wedged in between these columnar epithelia that are the motor of this mucosal escalator or elevator or whatever you want to call it, we have mucus cells, and otherwise known as goblet cells. These are cells that are actually producing the mucus and relieving it onto the surface of the epithelium. All right, just kind of zipping along through all this. If you were to look at the tracheal epithelium, you would see this mosaic of the different columnar ciliated epithelial cells interspersed with several of these goblet cells or mucus cells that are arranged throughout. There are also deeper mucus glands because these goblet cells are not able to produce enough mucus on their own down in the lamina propria. So I guess you would remember that mucosa is one of the four tissue membranes, the four types of tissue membranes we talked about. And that connective tissue layer of that tissue membrane, the lamina propria, in the trachea, has embedded in it these mucus glands that produce more mucus to supplement that of the goblet cells, and then they have apertures that emerge from the ducts of those mucus glands onto the surface of the tracheal epithelium. Mucociliary escalator. That sounds a little bit less disgusting than a mucus escalator. All right. So we sort of already covered each of these in that first, but I guess not. No, this is just the lung, right? So not only are lungs responsible for gas exchange, but they're also critically important in regulating the acid-base balance of the body, specifically by blowing off CO2. This is critical. So when you die, when an organism dies, it's not just the lack of oxygen that you have that leads to the degradation of tissue, because oxygen is what's giving, is allowing your cells to be metabolically active and burn energy. But it's actually the removal of carbon dioxide as the cells continue to expend their metabolic energy after the cessation of breath. Carbon dioxide goes up, that is going to increase the hydrogen ion concentration, make the body more acidic, And as the body becomes more acidic, it is more prone to opportunistic pathogens, bacteria that like an acid environment. So it's really important to maintain the acid-base balance in the body, specifically through exhalation of carbon dioxide, removing that potential source of acid in the body. So the lungs also defend against various pathogens. We're inhaling all this air all the time, these inhaled particles. Because of this, the lungs are richly invested with white blood cells, eosinophils in particular, and cells that produce antibodies, specifically, a range of antibodies, a lot of IgE, but various antibodies. It also acts as a blood reservoir. 20% of your total blood volume is in your lungs. That's a huge amount just in your lungs. That's a lot of blood just in the lungs. And then lastly, it is the site for the biosynthesis of leukotrienes. This is where we can activate angiotensin from angiotensinogen. We'll talk about that a little bit at some point. We also catabolize epinephrine and serotonin at the lungs. We'll talk about the lungs a little bit in the renal chapter as well, the hormone function of the lungs there. So there is a significant endocrine function in the lungs, specifically centered around the leukotrienes. So, all right. What does it look like? Let's take a walk down to the micro structure of the lungs, the microanatomy of the lungs. Well, we start at the trachea, walk down through a primary bronchus, and then every branch point that you walk past at that, it goes from primary to secondary bronchus, tertiary, etc. At a certain point, we get to these smaller bronchi, and once the cartilage plaques, the little cartilage plates that you see on the bronchi, end, we go into bronchioles. And lastly, the last bronchiole that you'll run into is called the terminal bronchiole. This is the last bronchiole that you'll have before respiration actually begins. You pass from a terminal bronchiole into what's called a respiratory bronchiole. A respiratory bronchiole is still going to be a tube shape, but it's going to begin to have alveoli, these little pouches coming off of it, which is where gas exchange actually happens. So down this tree, the bronchi that are in the middle of the tree are the principal site of air resistance. And they receive a significant, the smooth muscle in in those bronchioles receive a significant amount of innervation from the autonomic nervous system, the sympathetics and the parasympathetics. And they're also susceptible to any kind of inspired irritant, maybe diesel gas fumes or exhaust fumes, or I don't know, cat dander, unfortunately dog dander for me, that kind of thing. So, and that's going to change the diameter of those bronchi. If you have bronchodilation, that is the opening of those airways, that's being stimulated by the sympathetic autonomics. And so that this is the fight or flight. This is so you can move more lung to the air to the exchange surfaces. Bronchoconstriction is mediated by the parasympathetic nervous system, and just making those apertures smaller. You guys with me here? Pretty straightforward. All right. Bronchitis. I imagine everybody in here has probably had bronchitis at some point in their lives. There can be viral or bacterial infection in your lungs that'll give you a cough, sometimes it can be associated with phlegm or not, dry cough, what have you. And that's a normal part of life on Earth. However, about 10 million people have a chronic form of bronchitis called COPD, chronic occlusive pulmonary disease. Most of these people are older, and a large majority of people with COPD, the vast majority, in fact, have it because of why? Smoking. Yeah, smoking, COPD. In fact, over 40,000 people a year die from COPD. So I'm going to talk about lung cancer more on Friday. I won't bang that drum too hard right now, but hopefully no one in this classroom smokes. If you do, we can help you. Let's talk. Asthma. Does anybody in here have asthma? I actually have been developing asthma in the last year because we got a puppy dog that turns out that I'm allergic to. Asthma is a chronic atopic disease, and there are several manifestations of atopic disease. For example, atopic dermatitis is a form of skin irritation. Asthma, atopic rhinitis, also commonly called hay fever. But there are other atopic manifestations. You can have atopic problems of the eyes, so itchy, watery, irritated eyes. You can have atopic gastritis, so problems with your GI tract. All of them are, if you think about all of those different manifestations of allergic disease, those are all the surfaces with which you come into contact with the outside world, right? Your gut, things you eat, your skin, your eyes, your lungs, your nasal passages. So we won't get into the immunology of that too much, but it's a pretty interesting story. Anyways, within the lungs, asthma leads to a inflammation in the bronchioles, a thickening of the mucosal epithelia in the bronchioles, and then a constriction of the smooth muscles. It makes it quite hard to breathe. I didn't get a chance in the I would have talked about it in the CNS chapter. I didn't get a chance to talk about the different types of receptors. But albuterol is often administered to people in the midst of an asthmatic reaction. It's a beta-adrenergic bronchodilator. It is going to target the autonomic receptors on these smooth muscle cells and release them, and basically elicit the same response as you would from the sympathetic nervous system, and allow air to pass into the lungs once again. Yeah.
If you had normal breathing, or if you had just like a normal, would it improve that?
Well, yeah. So there are people who there has been use of various bronchodilators, or also like ephedrine, for example, stimulates. It's a beta-2 adrenergic agonist, and that can, sometimes athletes will do that before a performance of some sort, before an exertion, because it will increase bronchodilation and can increase ventilation. It's not really so in professional sports that is illegal and and frowned upon, and not really very healthy in the long term for the person doing that. But yeah, it's certainly done. It certainly is.
Your blood VO2.
What's that?
Increase your blood VO2.
Your VO2 max is going to be a function of It's more a function. It is a cardiopulmonary measure, but it's more a measure of cardiovascular efficiency. Yeah. It would help you reach VO2 max more readily, is what it would do. All right. Any other questions? Those are good questions. Anything else? All right. So one thing that many people are not aware of is that the lungs, the bronchi and lobules of lungs have actually two complete sets of vasculature. And the only other organ that's quite like that is the liver. It's not exactly like that, but at least in the liver, in the paintings of the liver, the drawings of the liver, all of the blue vessels are deoxygenated blood, and all the red vessels are oxygenated blood. Or all the arteries are red and all the veins are blue. Here, it's not the case. One set of vasculature, so the pulmonary arteries that are bringing blood from the right side of the heart to the lungs to get oxygenated, that's deoxy blood. So those are blue in this. That's bringing blood to the lungs to get oxygenated. However, lung tissue is just like any other tissue itself. Yes, ma'am?
So when you say complete set of vasculature, you mean there's like one artery that feeds?
There is a pulmonary artery and a pulmonary vein, and there is a bronchial artery and a bronchial vein. That's what I mean. So complete meaning both the afferent and efferent blood supply, right? There's going to be an arterial supply and a venous supply. That one being pulmonary, meaning that it's going to the lungs to be oxygenated, and another bronchial. So that's a set of arteries and veins that are bringing oxygenated blood to the lungs, to the bronchial tissue itself, to supply that tissue with the blood that it needs to be metabolically active. And then bronchial veins are draining that different blood, which did not go to the lungs to be oxygenated. It's in fact is already oxygenated, and it's coming in so that it can bring blood to the other tissue in the lungs that's not actually right at the exchange surface, right? So there's a lot of the tissue in the bronchioles right here. There's all this smooth muscle fiber and the mucosal epithelium and the connective tissue, the lamina propria. All that tissue is going to need oxygen as well, and nutrients, other nutrients that it can't just get by diffusion from the lungs. So there is vasculature that's coming to specifically supply that tissue with its metabolic needs. Does that make sense? So complete just meaning like artery and vein for both. Yep. Anyone else? So pulmonary blood pressure is actually quite low. It's only 30 millimeters of mercury, which is significantly lower. It's probably only maybe 25% of, in general, the pulmonary blood pressure is about 25% that of the systemic circulation. And because of that, because it's a low pressure zone, the pulmonary arteries, the vessels, are readily blocked by whatever is getting pumped through there. It's susceptible to clots, little fat globules that end up in your blood somehow, or air bubbles, etc. These are called pulmonary embolisms. One important way that pulmonary embolisms arise is through a patent foramen ovale. So I talked a little bit about the hole in the wall of the atria between the right and left that is left over from fetal circulation. If it doesn't seal completely after birth, then you have what's called a patent foramen ovale, and that is highly correlated with these pulmonary embolisms. I think the statistic is like one in 20 people. It may even be higher than that. I forget the exact number now, but there's a high occurrence of PFOs, so it's not an unheard of problem here. Well, that's it. next time, we're going to pick up here and talk about gas exchange in the respiratory bronchioles. And then I'll move from there into hemoglobin.